Okay, so let's begin. So today is the second lecture of this 21 lecture course, and let's get started. So last time we were talking about the galaxy morphology, and we talked about Edwin Hubble classification scheme about producing some order into galaxies. I think somebody is unmuted, so please mute yourself if you are on the call. Right. So Edwin Hubble wrote a book in 1936, which was called The Realm of the Nebulae. And it is in this book that he first introduced a version of this figure, which we now know as the Hubble tuning fork diagram. Now, the interesting thing about this diagram is that it tries to encapsulate a lot of things about galaxy morphology into one single figure. Because it is shaped like a tuning fork, it's referred to as the Hubble tuning fork diagram. On the left are ellipticals indicated by these letters E, E0, E3, and so on. As you can see on the extreme left is a perfectly spherical elliptical galaxy. And as you go to the right along the arm of the tuning fork, you see that the ellipticals become less circular and more strongly elliptical. At the junction of the tuning fork, you have a category which is called S0. S0s are also referred to as lenticular galaxies. We will come to that in a minute. And beyond this point, the galaxy arm splits into two. One shown on top, SA, SB, SC, are all spiral galaxies, but these are unbarred spiral galaxies. They don't have a bar at the center. And on the other hand, on the other arm, you have what are called as the barred spiral galaxies. SBA, SBB, SBC, there's even SD and SBD and so on. So what is changing as you go from left to right in the figure? What is visually changing, forget the physical properties, but what is visually changing as you go from left to right is the relative size and luminosity of what we call as the bulge. So the elliptical galaxy is a three-dimensional structure, okay, which we refer to as something which is 100% bulge. As you go toward from left to right, the fraction of the bulge goes on decreasing until when you reach SC or SD galaxies, the bulge is very weak. It's very small, it's very low luminosity, it's very weak bulge is what you see. So this is one of the things that changes. Within the spiral, within each of these arms of the tuning fork, as you go to the right, the bulge decreases, but also the arm openness increases, which means for SA galaxies, the arms are all tightly wound around each other. And as you go to SC and SD galaxies, they become more open. But this other trend of having decreasing bulge continues throughout. And of course, on the other arm, they are identical. So the SA and SBA galaxies are identical to each other, except that one of them contains a bar and the other does not. Now, there is also this diagram. If it were only a sort of structural or visual morphology difference, it wouldn't have been very useful. But as it turns out, it correlates very nicely with many other properties of galaxies, like how much gas do they have, what is their star formation rate, what is their molecular gas content, what is their stellar mass, and so on. So because of this, this diagram becomes useful. So just like the Hertzsprung-Russell diagram is an important diagram when you're trying to study stars, the Hubble tuning fork diagram becomes quite useful as when we try to study galaxies. And here what we are trying to do is that we are going to revisit this diagram several times in this course. Every 3 or 4 lectures, it will appear again in a slightly different avatar, so that you can connect what you have learned with what is known about the position of galaxies on this Hubble tuning fork diagram. Okay, so now we are going to look at galaxy morphologies one by one. First, let's look at ellipticals. Elliptical galaxy, this is an optical image of elliptical galaxy. And if you're looking at data from galaxy surveys today, you'll be easily able to identify this galaxy by several things, one of which is its color. So you can see that the color is going to be sort of yellowish, reddish in color. On the other hand, if you looked at spirals, for example, you would see that spirals have blue, lots of blue color, primarily in their spiral arms. The other thing which you see visually here is that the elliptical galaxy is very smooth and featureless. Okay, there's no structure, there are no spiral arms, there's no variation. It is a monotonically varying. The light distribution is a monotonic function of distance from the center. Of course, they can have different ellipticities. You can have a perfectly spherical elliptical also, and you can have slightly more elliptical galaxies like you see here. Elliptical galaxies form about 20% of field galaxies in the universe. So when you think of the universe, the distribution of galaxies within the universe and the environment of these galaxies, we talk of 3 different regions. One is called the field region, where the density, the volume density of galaxies is quite low. Okay, slightly higher densities correspond to what are called galaxy groups, and the Milky Way is an example of galaxies sitting in a group. If you go to much higher densities than a galaxy group, we talk of galaxy clusters. So we are going to study each of these in some detail later on, but this is just nomenclature. Low density regions means field galaxies, medium density means groups, and high density of galaxies means galaxy clusters. So if you look at field galaxies, only about 20% of the galaxies are ellipticals. About 70% are spirals, and 10% are the rest. But most ellipticals are in clusters. Most of the ellipticals in the universe are usually found in dense environments, and in clusters, particularly near the center of the cluster, the fraction of elliptical galaxies is very high. It can be 70%, 80%, 85%, and so on. Within the ellipticals, there are a number of subtypes, and they have their formation and evolution sometimes needs to be understood somewhat differently. They don't share an exact identical formation and evolution process. So first of all, field ellipticals, which we refer to as normal ellipticals. The picture that I showed you earlier was of one such field elliptical. These are distributed in low density regions also, but they are not very numerous as a fraction of the galaxies. But invariably, if you look at clusters at the center of mass of each cluster, you will invariably find a big, bright elliptical galaxy. And such galaxies are referred to as CD galaxies. So that term is given there. And these are massive, bright ellipticals that sit at the centers of galaxy clusters. And there is some correlation between the mass of the cluster and the mass of the CD galaxy that sits at its center. Typically, more massive CD galaxies are found at the centers of more massive galaxy clusters. If you look at high redshift, sometimes you don't see the CD galaxy because we are looking far back enough in time that the CD galaxy has not yet formed. So you don't see a CD galaxy. But if you take a very low redshift cluster, especially a massive one, you'll invariably be able to identify the CD galaxy. And sometimes it can be just obvious. I mean, I can show you a picture of a cluster and say which is the CD galaxy, and you'll say this one.
Sir.
Then, so these are the most massive ellipticals known, the CD
Sir.
galaxies. At the other end of the mass distribution of elliptical galaxies, we have galaxies which are known as dwarf ellipticals. These are quite small, very low mass. And by low mass, one is talking of roughly 10 raised to 8 solar masses or thereabouts. A related class of galaxies are known as dwarf spheroidals. They are usually found at the extreme faint end of dwarf ellipticals. So they're very, very low, small size, very low mass, and very low luminosity. And these galaxies are almost borderline with massive globular clusters in terms of their mass, right? And so they're also evolutionarily related to globular clusters. So they're basically things that are really borderline in being called a galaxy. They're almost always spherical, just like globular clusters. Dwarf spheroidals are spherical. That's why they're called spheroidals. Then they don't show high ellipticity. What is common to all elliptical galaxies is that these are completely smooth and featureless, as we saw in the image. There is no disk. There's no second component, just a single three-dimensional component. There are no spiral arms visible. There are no dust lanes visible. And they are generally lacking in cool gas. And as you have learned probably in an earlier course, molecular gas, cold gas, is something that is a prerequisite for the formation of stars in galaxies. And since there is very little cool gas in ellipticals, there are very few young blue stars. And that's why that color is yellowish, reddish in color. There are no blue stars. They're are denoted by letter E and a number N after that, where B by A, which is the ratio of the semi-major axis, semi-minor axis to the semi-major axis of the ellipse, is equal to 1 by 1 minus N by 10. So for example, an E4 galaxy, where N is obviously 4, will have a B by A ratio of 0.6. And E0s, of course, have a circular isoforms. They're completely spherical objects. Thing to remember is that the bulge component is a complete three-dimensional structure. It has, it may have some symmetries. It may be an oblate spheroid, maybe a prolate spheroid, or it may be even triaxial in a few cases. By triaxial, one means that it's elliptical in all three directions. So A, B, and C are the three orthogonal semi-majors, intermediate axis, and the major axis. Okay.
Sir.
Yeah.
Can you hear me? Yeah. What is
the
galaxy?
I can hear you. Go ahead.
What is the galaxy distribution in terms of redshifts?
How does it? How is the galaxy distribution in terms of redshifts? We will come to that. Okay, in various different ways during the course. But to answer it very briefly, many of the galaxies that we see in abundance in the local universe have all formed relatively recently. So the massive CD galaxies are recent. Okay, the grand design spiral galaxies like the Milky Way, they are also very recent. So when you go to higher redshifts, suppose you go to redshift 1 or 2 or 3, you will find that all these things that I have said are not strictly valid. And we will look at the progenitors of CD galaxies. We will look at the progenitors of today's spiral galaxies and how they form and evolve. But really, whatever I'm saying in this slide and in the next few slides should be strictly thought of as something happening in the local universe or the nearby universe. So by local universe, one probably means something like the local group. If you want to think in terms of megaparsecs, then a few tens of megaparsec is what you call as the local volume. And that includes basically galaxies within the local group and nearby clusters. So nearby universe maybe goes out to redshift of about 0.1 or so, which will include all the Virgo cluster, Coma cluster, and several other clusters, and so on. Then once you go beyond that, one talks of the intermediate redshift or moderate redshifts beyond 0.1 to say redshift 1 or so. And beyond 1, one will refer to as the high redshift universe. So your question is very important. We will revisit it in various ways about what is the distribution relative fraction at different redshifts. Huh? CD doesn't stand for anything. It was just some categorization about of these galaxies. It was just a label like A, B, C, D kind of thing. And it turned out that that CD label was assigned to these massive ellipticals. So when you say to an astronomer, this is a CD galaxy, they know what you mean. Okay, just like if you say this is a Wolf-Rayet star or something like that, they know what is meant. Okay, right. So you have a second category, which we saw in our Hubble tuning fork diagram, which is a lenticular galaxy. And this is an edge-on view of a lenticular galaxy. And as you can readily see that there is this sort of central region, okay, which is the bulge. Right, you have this central whitish looking region, which is the bulge, which almost looks like an elliptical galaxy that you saw previously. But there is another component over here, which is called as the disk. The essential difference between the bulge and the disk in terms of visual morphology is that the disk is essentially a two-dimensional structure. Its thickness is very, very small compared to its diameter. The diameter is sometimes 100 times, 200 times the thickness of the disk. So it's not obviously truly two-dimensional, but relative to its diameter, its thickness is very, very small. The disk that you see here is seen edge on. So now the disk, it turns out, which we again see when we discuss dynamics, that the disk is almost always circular. Okay, it is not elliptical. The disk is circular. So as your viewing angle changes, okay, so just imagine a circular object and you're changing, turning the paper around, you'll see it as an ellipse, right? And with the major axis remaining unchanged, but the minor axis becoming smaller and smaller as you turn the viewing angle around. So what you're seeing here is a galaxy which is nearly edge on. So this is called as an edge on view of the disk. You're seeing it almost like that. So that's why it is showing very little thickness, right? If you turned it around and saw it face on, you would have seen it as a circular object. So think of the disk as a saucer-shaped circular object, not very thick, but quite large in diameter. Now, the difference between ellipticals and lenticulars is obvious. It's the presence or absence of a disk. This is a huge disk. Sometimes it can be a little bit difficult to separate these two because it may be a lenticular with a weak disk. Now, if it's a very weak disk, do you call it elliptical? Or you make a more sensitive observation, you detect the disk and you call it lenticular. So there can be a little bit of ambiguity there, but this of course is an extreme example. There is no doubt that this is not an elliptical. So these lenticulars are characterized by the presence of a central bulge and a disk, okay, and the complete absence of spiral arms. And that indicates that there is little or no ongoing star formation in these galaxies. So ellipticals are also the same, lenticulars are also the same. They don't have much star formation happening. And as we shall again revisit later, these have properties that are intermediate between the properties of spiral galaxies and elliptical galaxies. So if you say, take any parameter like luminosity of the disk. In the ellipticals, it will be 0. In lenticulars, it will be there, but it will be less than what it is in spirals. If you take some other parameter like star formation rate in the galaxy, it will be very low in ellipticals, it will be intermediate in lenticulars, and it will be quite high in spirals. Now, remember, these are only statistical trends. There are sometimes exceptions. There are like highly star forming ellipticals, or there are spirals which we refer to as red spirals, which are extremely low star formation rate spirals. So there are outliers, there are exceptions to this pattern, but the broad pattern holds. So this is a kind of a spiral galaxy, somewhat similar to our own. It's called what is referred to as a grand design spiral. And in this particular galaxy, we are now viewing the disk face on, right? So you're seeing it almost circular. And unlike lenticulars, which have a featureless disk, or maybe some amount of dust in the disk like we saw. So you see these black regions over here. That's because there is some amount of dust in the disk of this lenticular galaxy. Whereas here, of course, there's dust, but there is also a lot of stars being formed. And the stars are being formed in the arms of the in the spiral arms of this galaxy, and therefore that is glowing bright, right? Okay, these galaxies can become grand design spirals, can become very, very large in size. The Milky Way is a good example of a grand design spiral. It's actually a barred grand design spiral, unlike this one. But it's a very good example of a massive grand design spiral. This complete Ferris wheel kind of structure, okay? One arm going all the way around and another arm going all the way around. And so, it's not present. I'll show you one example of a non-grand design spiral. You'll understand immediately. Okay. Before we go there, what is the diameter of the Milky Way galaxy? Can someone tell me? 1 lakh light years. That's correct. So it's about 30 kiloparsec, or approximately 1 lakh light years. That's the diameter of the Milky Way. It's really huge. Okay, so for scale, if you say that, you know that the nearest star is 4 light years away, but the Milky Way itself is 1 lakh light years. So if you build a scale model of the galaxy, you place the sun here and you place, you can work it out, you place it say 4 centimeters away, you work out what's going to be the size of diameter of the Milky Way. It's going to be quite large, right? Okay. So this is the non-grand design spiral. Okay. This is a photograph taken of this flocculent spiral, NGC 2775. And this clearly tells you what's happening here. Here, there is some spiral-like structure in the sense that there are regions where there is enhanced star formation, but there are no well-defined spiral arms, and they certainly don't emanate from near the center like we saw in the grand design spiral. This flocculent spiral is pretty unique in the sense that it seems to have a very large bulge, unusually large bulge. Normal flocculent spirals will have that central yellowish looking bulge region to be much smaller in size. This is I mean, that's why people are trying to study this galaxy and try and understand what's going on. But this is a unusually large bulge, but the structure outside is that flocculent structure. Star formation is happening there. Okay, usually at a lower level than what you see in the grand design spirals. But these galaxies, flocculent spirals, need to be understood differently from the grand design spirals. We'll come to that when we talk of how the spiral arms are formed physically. You will see how these things are different. A flocculent spiral is hard to place on the Hubble tuning fork, but you can check how tight. So there is no well-defined spiral arm, but still there is a kind of a structure. There's a pattern to it. You can't call it an arm, but it's not completely randomly distributed patches. So depending on the tightness of the spiral arms, you could try and classify this into the Hubble pattern. We'll come to the limitations towards the end of this lecture. We'll come to the limitations of the Hubble tuning fork diagram. There are some galaxies which don't fit in. This galaxy is an extreme example of a flocculent spiral. Most others, you can the bulge is much smaller, so that you see much more of the spiral arm-like structure. But so I think this will be difficult to classify this into the Hubble diagram, this particular galaxy. But other flocculent spirals, depending on the openness of their spiral arms, can be classified. Okay. So spiral galaxies, of course, are named as such for their bright spiral arms, which are prominent due to emission from bright O and B type stars. Okay. And this constitutes evidence for recent star formation. Okay. They're also prominent because of absorption from dust. So there are dust lanes within the spiral arms, and that creates for you a certain contrast, which makes the spiral arms stand out even further. So which are more massive, O and B, between O and B type stars? O type stars. They are the most massive galaxy stars known. They are very short-lived stars. Okay. Right. B type stars are somewhat less massive, but again quite massive. And in those spiral arms, you will often hear those star-forming clumps, which are there within each spiral arm, are often referred to as OB associations, because they are dominated, the light at least is dominated by OB stars. There may be other stars in the OB association, but O and B type stars are much more luminous than normal stars like the sun. So even if you have one O type star, it can easily outshine 1,000 sun-like stars. Very luminous. Yes, so this also explains why the color of the spiral arms is blue, because we know that O and B stars have extremely hot surface temperatures, making their Planck spectrum peak at blue wavelengths, and therefore you find them to be blue in color. Lots of blue photons there. They're also bright, interestingly and expectedly, in the UV light. So if you take a UV image of a galaxy, you'll see the spiral arms very prominently. Okay, right. So so suppose the nearest spiral galaxy, large spiral galaxy to us, is the Andromeda galaxy. It's very big. It subtends an angle of about 5 degrees on the sky. Okay, and it is 67 kiloparsecs in diameter. Okay, so how will you calculate its distance? Suppose you know how big it is. Suppose it had subtended 1 radian on the sky. What would be its distance? Anyone here on the Zoom call? Suppose it were even larger. It is subtending 1 radian on the sky. What would be the distance?
67 kiloparsec.
Yeah, it would be 67 kiloparsec. Now it is subtending 1/10 roughly, or a little less than that, radians. So it will be about 10 times more distant, right? 670 or a little more than that. So if you do the exact calculation, you will find that the distance comes out to be 780 kiloparsec. Of course, the size has distance has not been determined in this way. What we've do in practice is that we first determine the distance using Cepheid variables or some other technique, and then we use the angle subtended to calculate the diameter. But just as an exercise, I've told you. So that's the sort of size scale of the local group, about a megaparsec or so. Incidentally, Andromeda, and we'll see that later, Andromeda and Milky Way are currently moving towards each other. So if you take a spectrum of Andromeda, you'll find that the spectrum is blue shifted, right? Okay. Right. So one more concept that is quite useful is in determining age of clusters. So you know that much of the star formation that happens in these spiral arms happens in what are called open clusters. And this is a concept that you should know, that you can use the main sequence turnoff to calculate the age of open clusters. So can someone tell me how this is done? Okay, let me simplify the question. There are two clusters, say M67 and Pleiades. Okay, which one of them is a young cluster and which one is old? Sorry?
The more massive will leave the track before.
More massive what?
More massive will leave that track soon.
Yes. So more massive stars will
Hello,
leave
sir.
yeah, sorry. Yeah, more massive stars will leave the main sequence earlier. Okay. So if that main sequence starts getting truncated here and here. So assuming all the stars in the open cluster formed in one event at one point in time, t equal to t naught, then as the cluster ages, the more and more stars will start dropping off the main sequence. First, the more massive stars will leave the main sequence, and eventually the less massive stars will leave the main sequence. So clearly, as a cluster, M67 is going to be an older cluster than the Pleiades. And so by knowing how long stars of a given mass, absolute magnitude and color spend on the main sequence, one can constrain exactly the age of the coma cluster, the M41 cluster, and so on, by simply plotting the absolute visual magnitude and the color of individual stars in that cluster. Right. Okay. So let us now look at the mass to light ratio of stars, and we will use that to understand the mass to light concept of the mass to light ratio of galaxies. So for main sequence stars, the luminosity scales with mass as m raised to 3.5. You might remember this from your stellar structure course. So now if you just rewrite it as m over L, then m over L will scale as m raised to minus 2.5 or as L raised to minus 0.71, showing, as one expects, that the later spectral types, which means K and M type stars, have a higher mass to light ratio. We knew that For K stars, the mass to light ratio, given that they have about 0.4 for 40% the mass of the sun, gives you a mass to light ratio of 10. On the other hand, A-type stars, which have a mass of typically of 2.5 times the mass of the sun, have a mass to light ratio of 0.1. So although their mass ratio of K to M stars is less than a factor of 10, because of the steep dependence of luminosity on mass, the mass to light ratio has varied by a factor of 100. This is for individual stars. Now, can we define the mass to light ratio of a galaxy? Yes, we can. Here, instead of taking the mass as the mass of one star, we just add up the masses of all stars in the galaxy. And for luminosity, we do similarly. We just add up all the luminosities together to get the total luminosity. So the total mass of the galaxy and the total luminosity. What is the unit of mass to light ratio? It's a unitless quantity because mass is measured in units of solar masses and luminosity is always measured in units of solar luminosity. So the luminosity mass is actually mass divided by m sun, and L is L divided by L sun. And so both quantities are unitless. Their ratio is also unitless. There's no unit, just a number. For galaxies, mass to light ratio reflects the average mass to light ratio over the population. Within galaxies, we have two types of stars typically. One are called population 1 stars. These are young stars. In these population 1 stars, massive stars dominate the light, but low mass stars dominate the mass. Since these galaxies, since these population 1 stars are very young, they're usually still on the main sequence. They're not left the main sequence. But if you take the older population of stars, which we refer to as the population 2 stars, these, at least the more massive stars in this population 2 have all left the main sequence and have become giants, right? And so the giants are the ones, you know, that in the giant phase, most stars become very luminous, not because their temperature goes up, but because their diameter increases drastically. So in population 2 stars, which are these old stars, the giants dominate the light and the main sequence stars dominate the mass. Primarily because main sequence stars which are still on the main sequence are typically low mass stars, and low mass stars always dominate in sheer numbers relative to high mass stars. We'll look at the initial mass function and things like that in a later lecture. So if you look at a typical spiral galaxy, and by typical I mean really it's a bit misleading in the sense that very often in the literature and in textbooks, etc., people will talk of typical spiral galaxy. And actually what they mean in reality is a Milky Way-like galaxy, which is actually quite atypical, quite rare. Milky Way sits almost at the top end in terms of mass and luminosity of spiral galaxies. It's a very big, massive, highly luminous, highly star-forming kind of galaxy. 90% of spirals are, 95% of spirals are less luminous than the Milky Way. So just take that a little bit with caution. So in the typical spiral galaxy, which means Milky Way-like galaxies, and within the solar neighborhood, we have a mass to light ratio of 6. The suffix V indicates that the luminosity is measured in the V band. It is very hard for us to measure the bolometric luminosity of galaxies So typically we do make a proxy and we measure the only the luminosity in a particular filter in a particular wave band. It can vary, therefore it can vary if you change the filter. So if you go use the luminosity in the B band, the same number comes out as 10 in the solar neighborhood. In general, mass to light ratio increases with age and metallicity. Okay, why it increases with metallicity is a question that I will answer in one of the future lectures. Okay, metallicity, when we try to understand how the metallicity changes the luminosity of individual stars of a given mass. But given all this, the maximum range that you can have for the mass to light ratio of a galaxy is only between 2 and 20 if you use the P band. This is very different from what you had for stars. We already saw, we took a relatively low mass star and a relatively high mass stars, and we saw that the mass to light ratio of stars can vary by a factor of 100 quite easily. And even more, if you take O-type star and let's say M-type star, the mass to light ratio can be vary by more than a factor of 1,000. But here, it can't vary by more than a factor of 10. And that is because these outlier population at the high mass end are very rare. So when you average over the entire population, you don't get a very high range of the average mass to light ratio of the entire galaxy. Okay. So that usually stays within a factor of 10. What are population 3 stars? Zero metallicity. Where will you find them? Yes, so you'll find them at the very early universe. So these are like the first stars to form, and their metallicity was very, very low, extremely low, because the only metals they could possibly contain were metals from the primordial nucleosynthesis after the Big Bang. So very small amounts of lithium and so on, but essentially otherwise metal free. And these are the first stars that formed in the universe. Many of you must have heard about the launch of the James Webb Space Telescope. James Webb Space Telescope, one of its primary science goals is to directly detect the population's 3 stars. Okay, very low, very high redshift, very high luminosity, but very, very rare objects which have to be searched for at extremely high redshift. Okay, yeah. Yes. Yeah, because you're thinking in terms of a single generation of stars. So many population 1 stars. So tell me first, is the sun population 1 or population 2? Is it high metallicity or low metallicity? Let me ask. It's high metallicity stars. Okay. In fact, that may be one of the reasons why we live on a high metallicity planet, right? We are not a hydrogen and helium planet. We are a everything else planet. So we are a high metallicity, 100% metallicity. That's because the sun, from which the Earth is born, is a high metallicity star. Correct. It's a second generation star. So it is not a first generation star. And many of the population 1 stars are second generation stars. Whereas the population 1 stars are often the remnants of the first generation. They formed a long time ago. They're very old, and so if you look at the mass function of population 1 and population 2 stars, you will find that the population 2 stars are truncated at the high mass end. There are no high mass population 2 stars. There can be high mass population 1 stars. Why? Because most of them have gone supernova and gone. So any surviving population 1 star is population 2 star is a low, intermediate to low mass star. Okay, right. Okay, so when you form stars inside any cluster, I said open cluster is the place where you form stars. You have to know the initial mass function. So what is the initial mass function? It's a normalized distribution in mass of the mass distribution of the stars at the time of their formation. Okay, so it specifies the distribution in mass of a newly formed stellar population and is frequently assumed to be a simple power law. Okay, so you assume that it's a simple power law of the mass. The reason why it's written as 1 plus x we'll come to later, because when you take the derivative star formation rate, then 1 etc. will go away. But just a way of referring to the initial mass function, and that number x is your parameter which you need to fix the index of the power law, which you can fix via observation. So you can take a nearby open cluster or take 10 nearby open clusters. You measure the mass distribution for all of them. You have to make sure you try to find young clusters, because if they're not young, what will happen is the high mass end will start getting truncated of the initial mass function. So it's no longer initial, it's just a mass function. So every mass function, including an initial mass function, this power law does not hold over all masses, because it extends from a lower mass to a upper mass. There will be some lower mass, M1. There will be some upper mass cutoff. Okay. The lower mass, what causes a lower mass cutoff?
The nuclear
Yeah, go ahead.
the nuclear fusion, the pressure required for the temperature and pressure required for
Correct,
nuclear.
correct. So that is absolutely right. The temperature, you need a certain temperature to be reached for nuclear fusion to start. And if the gas cloud, or which is a protostar, whatever you want to call it, if that mass is very low, then the temperature at the core will never be high enough to fuse hydrogen into helium, and that will be a failed star, right? So therefore you have a low mass cutoff, and that is typically about 1/10 solar masses, or a little bit above that or below that, one doesn't know exactly. For context, the Jupiter, okay, is much lower than that. If it is slightly lower than that, than this sort of cutoff in mass, then you get what is called as a brown dwarf. And then you get these giant planets like Jupiter, which is like orders of magnitude below the cutoff. Right. What causes an upper mass cutoff?
Radiation pressure, I guess. The radiation.
Yes, radiation pressure, correct. So you must have heard of the Eddington luminosity of stars. And so what happens is, remember, there's a scaling, strong scaling between mass and the luminosity as a function of mass. Eventually, the mass becomes so large and the luminosity becomes so huge that the star itself becomes unstable. And so there will be a mass cutoff. Now, there is a lot of debate in the literature about what this upper mass cutoff should be. But if you want a typical number, it's about 100 solar masses. Very hard to form stars above that. And the luminosity of those stars is just mind-bogglingly huge. Okay. So depending on what the index is and what the minimum and maximum mass values are, there are several different IMFs that are in wide use. Okay, the saltpeter IMF was the one that was first introduced by saltpeter in a paper in 1955. That is still quite commonly used. That goes from 0.1 solar masses to about 125 solar masses and gives you this value of X to be 1.35. Then other people came along after saltpeter and they said, no, this is too simplistic. We need to do a more careful measurement with open clusters, and that power law need not have the same slope all around. So they kept changing the slope over different mass ranges, is what you see here. And then there was the Miller and Scalo IMF, which was again a variant of the Scalo IMF. More recently, Chabrier and Krupa have introduced their own IMFs. Nowadays, you will find that most papers do use the Chabrier 2003 initial mass function. So you can go and, so this is, I mentioned in my first talk that sometimes I will point you to papers where you can read more. So just, if you want to just read up what the Chabrier IMF is, just go to ADS, search for Chabrier 2003, very highly cited paper. You'll get that. It's a very complex, it's a mix of both usually. The saltpeter IMF originally was a purely observational thing, but most of the more modern IMFs are a combination of models and observational fits to models and revised models and so on. So it is not, the models are mostly motivated by our knowledge of stars, the theoretical modeling of stars, which develop the models. And then the models may have some free parameters which get fixed by fitting to observation. So it's a hybrid sort of way of doing it. So there is a review by Bastien et al. 2010, which compares all these various IMFs and so on. There is a lot of debate in the literature about whether the IMF is universal in time. Okay? So is the IMF that we see in the local universe the same as the IMF in the high redshift universe? And people have, of course, varying views on this. I'm no expert on this, but there is a fair amount of debate. Okay. So you can ask yourself a question like, for saltpeter IMF, what is the relative number of K and A stars in a cluster that has just formed? So if you plug in the typical mass of a K star, which is 0.4 solar masses, and A star 2.5 solar masses into that formula, remember there's a 1 plus X in that formula. You can do this, work it out, and what you will find, I mean, you do this as a homework, what you will find that there is quite a dramatic increase in the relative number of K stars relative to A-type stars, although their mass varies by less than a factor of 10. So just like their luminosity changes very rapidly with mass, their relative numbers also change very rapidly with mass, but in the opposite direction. The low mass stars are always more common than the high mass stars. Okay. So sometimes if you look at the cores of spiral galaxies, you can see spiral structure therein as well. So those of you familiar with fractals would realize that this seems to be sort of fractal-like in nature, that as you zoom in, you keep on seeing the same kind of structure. So because the spiral structure is seen in many, many galaxies, you need to have some explanation of why it is formed, and when it is formed, why is it long-lived? Because if you have a spiral structure that forms and then gets washed out in a few million years, then you won't see many galaxies with spiral arms. But we see many, many galaxies with spiral arms. Even in the cores of galaxies, we see spiral. So this actual galaxy is not even fitting into the full image. It's much larger than that. But at the very core, you do see the spiral arms. So we talked about unbarred galaxies so far, but there are barred galaxies as well. These are roughly half of all these galaxies, Milky Way included, show a central bar which can contain up to 1/3 of the total light. Up to 1/3. It can be less than that. There are many galaxies with very weak bars, but up to 1/3 of the light. Bars are a form of dynamical instability in differentially rotating stellar disks. So we are going to when we look at dynamics, we'll understand a little more about how these bars form and how they can be sustained over long periods of time. Not just spiral galaxies, but zero lenticular galaxies can also have bars. And a bar can persist for a long time, even when it is composed only of stars, has no gas in it at all. By gas, one means whenever one talks of gas in galaxies, it's not the gas inside the star, because that's a plasma. One means gas outside of stars in the interstellar medium. Bar patterns are not static. They rotate with some speed, with a pattern speed, but unlike spiral arms, they are not density waves. So again, when we come to the dynamics of spiral arms, we will understand all of these terms. Don't worry too much about it. Stars in the bar stay in the bar, which is unlike spiral arms. Again, as we shall see later, a star that is formed in a spiral arm, almost all the stars in a spiral galaxy disk are formed inside spiral arms, but they may not be found inside spiral arms later on. So one good example is the sun. The sun formed 5 billion years ago inside a spiral arm, but right now it is not sitting inside a spiral, sitting outside a spiral. Because in fact, throughout its life, 5 billion years, it has passed through several spiral arms. So it goes into a spiral arm, comes out on the other side, and so on. And that is because spiral arms are believed to be density waves rather than static structures. The asymmetric gravitational forces of a disk allow gas to lose angular momentum, compressing the gas along the edge of the bar. And then this gas loses energy through dissipation and moves closer to the center of the galaxy. So we believe that in most bars, the bars act as a funnel for gas to flow towards the center of the galaxy. So you can often have galaxies where, because of the presence of the bar, there is enhanced star formation at the center of the galaxy, because a lot of gas is getting funneled from the outer regions of the galaxies through the bar into the central region where star formation happens. Yeah. So this is an example of a barred spiral galaxy. You can see that that sort of central structure. This is the bar. So this region is the bar region, and the spiral arms emanate. They start from the end of the bar. So where the bar ends over here, the spiral arm begins. So there's one spiral arm here, and there is one spiral arm here. Not all galaxies have such large, strong, luminous bars. Most of the bars are are relatively small and weak. They can even be buried deep inside the overall bulge. So you may not see them visually like this. This again, just like that flocculent spiral was an extreme example, this is a rather extreme example of a very, very strong bar. Such strong bars are very, very rare. Okay, so I'm going to stop now. And if there are any questions on any material we've covered in the last lecture or now, please ask.
Want to ask about this dwarf galaxies.
Yes, dwarf galaxies. Yes, go ahead, please.
Yeah, is only this mass limit 10 power minus 10 power 8 solar mass is only criteria to define dwarf elliptical galaxies?
Not really, because one way is to look at the environment. So, for example, if you have a very low mass object, right, but it is sitting, it is in orbit around a galaxy. So, for example, we know that around the Milky Way galaxy, there are several globular clusters, and they have typical masses of 10 raised to 6 solar masses. There are some globular clusters around other galaxies which we can see as well, but those are identified as globular clusters because they are in the proximity of a large galaxy and are often seen to be in orbit around it. So you have to look at the environment. So if you see a very low mass object and you see no other large galaxy in its vicinity, then you can make the claim that it's a genuine galaxy rather than a globular cluster. Otherwise, globular clusters and the extreme low mass spheroidal galaxies, dwarf spheroidal galaxies, have many similarities. Yes, but they may not see Milky Way. Suppose Milky Way is sitting in a central galaxy of a halo and it has some satellite galaxies. They'll be quite a bit larger than 10 raised to 8. The 10 raised to 8 is a rough number. Don't hold me to that. It could be 7.5 if you want.
So there is no, in terms of luminosity, there is no limit. Luminosity, in terms
Yes,
of luminosity.
Yeah, so mass and luminosity for these low mass objects are quite tightly correlated. So if I set 10 raised to 8 solar mass as the mass, then I will have the corresponding luminosity, which will not be very different from 10 raised to 8 solar luminosity. So you can have a cutoff either in terms of mass or in luminosity. You don't find such objects. See, there seems to be roughly an order of magnitude gap in terms of mass or luminosity between the most massive globular clusters that we know of and the least massive genuine galaxies that we know of. So there are very few objects that fall in that gap, whether you measure it in terms of luminosity or in terms of mass. Yeah.
So the one with models of the initial mass function.
Yes.
Can you go to that slide?
This one?
Yeah. So the second one, for a very small mass, the x is negative and has more magnitude of 1. So during that time, the number of stars will increase with mass and then it will decrease, right? So it will give a peak at particular value of mass.
Correct, correct.
So what's the reason behind that?
I don't actually know why, what the reason is, but you're right that there will be a turnaround it will not be a monotonic function. There will be a turnaround. Numbers as you go to lower and lower masses, you expect numbers to go up, but they will suddenly now decrease at the lower masses. I don't know. You'll have to read the Scalo paper to find out. You, Rashi, you had a question? What is the bulge in the spiral galaxy? It is very, we will look at it in more detail, but the bulge, in terms of many of its properties, the bulge of a spiral galaxy is no different from the bulge of elliptical galaxy. It is 100% bulge. It has no disk. Okay. So in many of their properties, they are very similar. And there is a reason for that, because we believe that the formation of processes for bulges in spiral galaxies are also related to the formation processes for elliptical galaxies. So it's no coincidence that their properties are very similar. But they're not identical, because unlike the bulge of an elliptical galaxy, which is fully exhausted of gas, it has no way to grow. These are what are called passively evolving galaxies, which means star formation, whatever was to happen has happened. Now things are running on autopilot. Nothing more is going to happen unless there is a galaxy merger event. In which case you could have a situation where you have an elliptical galaxy, nothing is happening, but some small gas-rich spiral galaxy falls into it. Now suddenly the elliptical galaxy has a new reservoir of gas, and star formation can restart. So there are blue ellipticals, for example, which are like ellipticals, except there is star formation going on at the center. So, but again, what I'm going to teach you in this course is the sort of broad pattern. What is the average? What is the median? There are going to be outliers, interesting objects at both extremes of every parameter we look at. So those have to be studied as individual objects to try and understand them. But what approach we are going to take in the course is try to study the average typical properties, not the properties of the extreme objects.
Hello.
Yeah.
Hello. Yeah.
Yeah,
So
please.
when we look at a particular galaxy, we can find the current mass function, right?
You cannot really find the current mass function because, I mean, observationally, because you can model it in various ways and try to determine it, but you can't measure it directly. Because remember, except for the Milky Way and with Hubble, for nearby galaxies like Andromeda, the stars are unresolved. So you cannot measure the mass and luminosity of individual stars. They're all merged together. So if I have 2 stars or 2000 stars whose mass and light is all merged, you can measure the mass separately, you can measure the light separately, but you cannot measure. So when I said take the mass of each star and add it up, take the star of each luminosity of each star and add it up, that is only in theory. In practice, you can't do that. There is no way to add the stars.
So how do we find the initial mass function of any galaxy?
You assume the initial mass function. See, there is no such thing as the initial mass function of the galaxy, because initial mass function refers to the formation in a galaxy cluster, open cluster, in the disk of the galaxy. What is the mass distribution at that time? It is not, because there are many such cluster formations in the disk through the lifetime of the galaxy. So you cannot speak of initial mass function of the galaxy. You can talk of the mass function of the galaxy, which means today, if I take the Milky Way, what is the distribution of masses of all stars in our galaxy? That is that is something that can be thought of. It will be hard to measure, but it is not something that